Orada bu müzik kayıt altına alınır. Kızlar makyajlarınıza dikkat edin. Saçıma bakayım. Sesim bu cihazdan geliyor mu benim sesim?
Abi senin şu anda zaten bir tane katıldığın şey var. Ondan geliyor.
Tam ses geliyor yani değil mi?
Geliyor geliyor.
Güzel.
Sorun yok.
Bu millet niye gelmiyor? Tek tek arayalım mı hepsini?
Bilmiyorum. Yani öyle bir şey. Ama bir tur daha çaldır gitsin bence.
Tamam, son bir defa ben çaldırıyorum. Ondan sonra başlayalım mecbur. Ne yapacağız?
Zehra şu anda ders var. Yayında. Evet, tamam. Zehra Zoom kuruyormuş. Şimdi öyleymiş o.
Valla siz pandemide derse girenler değilsiniz değil mi? Derse girenler olsaydınız
Yo,
her taraf.
pandemide derse girenlerdeniz.
O zaman annenin telefonundan girenlerdensiniz.
Evet. Küçük olduğumuz için o zaman. 4, 5, yo. Üçüncü, dördüncü sınıfa denk geliyor.
Tamam biz başlayalım arkadaşlar isterseniz de bir burada olduğunuzu belli edin en azından. Nurislam, Zeynep, Betül, Hümeyra, Emir, Faruk. Burada mısınız oğlum siz?
Evet buradayız. Güzel.
Başka kızlar burada değil mi? Ulan çete bir şey yazın bari ya.
Abi sesim geliyor mu?
Tamam erkekleri hallettik, kızlar ses vermiyor. Ah.
Bence abi sen başlayabilirsin. Zaten
İng-
kayıt alınıyor. Şey olursa bakarlar yani.
Ben İngilizce ile başlıyorum arkadaşlar. Eğer anlamakta sıkıntı çekerseniz en sonunda tekrar Türkçe'ye geçeriz. Ama bu İngilizce işini denemek istiyorum.
Abi sen bu İngilizce işini hazırlığın sonunda çözdün mü sonuna kadar?
Ne?
Ya sen hazırlığın sonunda istediğin gibi İngilizce konuşabiliyor muydun?
Hayır.
Ha, tamam.
İngilizce dilini geliştirmek istiyorsan bunu sürekli kullanman lazım. Yani öyle bir yıl çalıştım halloldu diye bir şey yok. Dil çalışarak hallolur, dil kullanarak hallolur. For example, I am still not that fluent in speaking English and I'm sometimes not that confident because it's a process, and it's harder to get over sometimes. It's an interesting idea to learn a new language rather than the one you taught when you were born. So for today's lecture, we'll be looking at at computers in general, because as you all know, we did a survey at the beginnings of this whole course thing that whether you wanted to learn more about computers in general or you want to pursue only the programming part that will be presented to you in Olympics. and you chose the first option. So we'll gonna start with by exploring how a computer works and what a computer actually is. And eğer beni gerçekten anlamayan varsa söylesin, kimsenin anlamayacağı bir dersi İngilizce konuşacağım uğruna yapmam. Tamam. Once you type computer on the internet, as you do for most things you research, you see images of machines, electronic and mechanical machines that are usually familiar to you. Like they have a screen, as you can see here, they have keyboard, they have mouses, or you may see a phone. And that may create an ambiguous term in your mind that a computer is basically a computer, the device that you always use to do messaging and many of your stuff nowadays. But computer actually is not a mechanical device by definition, or at least the first time it was defined, it was a mathematical object. A computer, as you can understand from its name, is a machine that computes something. Therefore, we have a action, an act of computing. We have this word in English, and we can also use it in Turkish as compute etmek, but computing is better to use here. And computing is a loosely defined word, which usually can be equal to calculate, but not entirely. It's a loosely defined term, as I said, but it generally means some list of operations in mathematics. To sum this up, there's multiplication, there's addition, there's subtraction, there's exponentials, there is square roots and other types of roots. By square roots, I mean karekökler, exponentials, üst alma, subtraction, addition, multiplication, toplama, çarpma, bölme, çıkarma. These are things that are in the space of computing, that are in the space of being computable. So if a machine can does these operations on something, on some sort of data, like numbers or the text you type in here, if a computer can do this on a set of data you provide to it, it is a computer. It is a machine that computes these things. As we can see here, and the idea was denoted by famous computer scientists, Alan Turing and his, maybe we cannot call it, his team. They started working on computers as a mainstream idea. Back then, computers were like crazy inventions that only rich people, rich hobbyists may pursue, and that will not do much practical aim in the real life. For example, you may look at the 19th century, and there was some lady whose name I forgot, who programmed the first computer, but it was a mechanical computer, meaning it operated not on circuits but on gears. Sort of this one, çarklar. She used gears to compute the outputs of differential türev equations, denklemleri. And then going into World War II, the Allies and the Axis had a very brutal fight, as you know, and Allies figured out a way to crack the code of those in Axis so that they can defeat them, which was achieved by the means of computers. They created a machine, an electronic machine, whose team was led by Alan Turing, to solve the code, the military code that Nazis used among themselves to communicate their plans. They used computers to crack this code, this password, you may recall. And that was the beginning of the computer science as a mainstream field that is pursued by people around the world. Eyvallah. And by that, we also brought about many philosophical and mathematical ideas. As we said, computing is a mathematical idea. Alan Turing published many articles, and his team, many articles on cryptology, even artificial intelligence, computer philosophy, computation, which is a field of mathematics, not computer science. you see lots of mathematical questions on your Olympiad because computer science is essentially based on mathematics. You will need to learn linear algebra, which is what computation is built upon. So that explains why these people dealt with mathematics and philosophy. And by philosophy, I mean, topics still in rise today, like is artificial intelligence going to be some sort of job killer or something? These kind of utopias or dystopias, utopyalar ve distopyalar. They talked about these things, and the computer science was set. And then, these famous machines that filled a room, not these ones, but the ones that were with room size and did not even have a kilobyte of RAM. For example, nowadays, 8 gigabytes of RAM is not enough for your computer to operate significantly. But back then, they ran a whole Nazi code cracking program with these things that only had a kilobyte of RAM, and that kilobyte of RAM was able to be fit into that room only because the circuits were brand new. Like, for example, you may recall this famous photo, the first transistor was huge, not like those nanometric scopes we use today. Like Apple has produced 3 nanometer chips. By 3 nanometer, they mean the size of that device on the processor of Apple computers. But back then, the transistors were that big, so they had to fill all of these with millions of those to create 1 kilobyte of RAM that was able to operate to crack the codes of the Nazis. And then going into the 70s and 80s, they were able to put together more significant computers like Commodore 64. Yeah, 64. So this computer was developed by IBM and then Windows. Abi ses seni rahatsız ediyor mu?
Yok, hayır.
Tamam, rahatsız ederse söyle lütfen. Başka bir içinde. Kolay gelsin. Commodore 64 and other kinds of computers, they were shrinking, in size by the time goes on, and they were increasing their RAM, their storage, their processor capacity, and it finally resulted in something called Unix. Unix is an operating system, which is a base for most operating systems today because it had brought about many revolutionary ideas with it. You must learn about this operating system, at least as a general cultural thing, because it's very important in computer science history. It had brought about with it the high level languages, by which I mean you needed to write back in the day code in assembly to program your computer, which was just something like that. This image is assembly code, and what this does basically, I don't know, I can't read it, but that many lines only are able to sum two numbers up. In a modern programming language, the only thing you need to subtract or sum up some things is this. You run this, and then it does the operation for you. But to do that in assembly, you needed to write many lines of code, and you needed to also be aware of the hardware you were using to not to exceed its limits. You needed to optimize your code. But with Unix, that became a history. They created a language which is pretty familiar to you, which must be pretty familiar to you. The C programming language. It was revolutionary back then, and it still is, to my opinion. You were able to do most of the things by a single line with that. So you had the space to create more complex programs now, rather than typing it all in lines and lines and lines of assembly code. To exemplify this best, we may show you Apollo source code. Apollo, you might recall, was the mission of the United States to travel to moon back in the 70s as part of I'm clicking the wrong thing, as part of the Cold War. And yeah, she was programmer behind Apollo, and they printed out all of the code Apollo executed in order to land on the moon and get the astronauts back on Earth. And they were the height of the programmer who wrote them. They were all in assembly, lines and lines and lines of code, and these papers are thin, believe me. That was the thing back then, but Unix eased what many of these. Unix eased many of these things. Another thing Unix introduced was modularity. Now, in order to program something, you need to produce an architecture for your software, because once a software goes beyond computing some, primitive operations, being a primitive calculator that can sum or subtract some numbers, it evolves into a more complex, very complex system of code that need to work together in order to execute something like this. Have a look at the screen. You have Brave now. Brave runs Google on this tab, and another tab, it runs Wikipedia. Another tab, it runs also Wikipedia. And this tab, Musiat. Why do I have Musiat here? And it also has add-ons here. I can add my dark reader and turn this on, and the page turns into dark mode. And then I have various other add-ons here. I have settings, I have crypto wallets, or at least Brave offers it, but I've removed it. There's something you may access is this is kind of some kind of crypto thing. You have bookmarks, you have lots of things on a software, and in order to execute these, do these all at the same time, you need to divide your software into various files that are needed to be centralized in one central file and be governed in their priority to simultaneously provide the user with whatever the services that the system needs to provide. You know what I mean? This modularity philosophy, their philosophies of computers, programming and so, was introduced with Unix, making programming larger and more complex programs easier. This was also the idea behind developing C, abstracting over the previous assembly and binary-based coding. For most fortune, to be honest, this was also a programming language which is also very low level to today's standards, and to today's standards everything's trash. Yeah, you needed to allocate your memory manually. And Unix got rid of all of that, at least for the casual programmer. As an operating system programmer, if you become one day, you'll need to adjust all of these things by your own there as well. So yeah, I'm reading some excuses about people not coming to the lecture. So Unix was that. And then they built on top of Unix with Linux, which I have right on my system, and I'm trying to show it by just ignore what I'm doing on the screen right now. But I have Linux here, and maybe some of you have Macs, which have installed Mac OS on them. These are all based on Unix. Their philosophy, their file system, for example, how the files are organized. Do I have Ranger here? Yeah, I have Ranger. For example, this is the structure of my file system. You see, I have at the root of my computer being boot, dev, EFI, AHC, home, lib folders. In your Windows system, you cannot find those, because in Windows system you have C and then kullanıcılar and then whatever your name is, and then pictures, for example, and then documents. And in Unix, like operating systems, we have those kinds of files. And then when you go to home and your username, you find your files. That's a file system difference between Windows and Unix-like operating systems, which involve mostly anything other than Windows. So we have an opponency with them. Why did this not install? Yeah. So I have Linux on my system here, which I very like to use because it's more configurable, it's free and fast, and also it's not tracking my data. Yeah, Arch Linux, point whatever. So that's the basic history of computers, and then there's internet, which resulted in CIA opening its local net into the whole world, and then there's artificial intelligence, there's graphics programming, which was boosted heavily by the development of computer games. There's also microchips, microcomputers. There are lots of things in the computing world, but programming sat there for the most of the time, being hopped around in various manners, but I think its time is coming to die with the approach of artificial intelligence, because most programmers today use artificial intelligence heavily to assist themselves in coding their programs. Not only that, but artificial intelligence is evolving, and the fact that I mentioned C abstracted out some of the components of the system so that you could program easier, more easily. But today's computer languages, programming languages like the notorious JavaScript, Go, Flutter, you may exemplify Dart, all of these programming language abstracted out the computer so much that it now became impossible to do something technical, to do something high level in your programming of a program, because everything is poured out in you. There are multiple APIs, libraries, application programming interfaces to use to program your software, and that leaves no work to you. That's why all of these websites are so inefficient. You keep buying more RAM for your computer, you keep buying computers with more storage, but by exponential increase in hardware, exponential üşengeçlik in programming comes. People tend to ignore optimization more, so they make more bloated programs. Bloated is a term for software that uses unnecessary amount of code to do its job, which eventually makes it inoptimized. Consume more RAM, more processor than it needs to, sometimes double, the quadruple, which is something we see a lot nowadays. These Brave browser is based on Chrome. Chrome is based on Chromium, and Chromium is the heart of Electron, which is a JavaScript library. And most of the graphical interfaces nowadays, like Spotify, WhatsApp, or we may exemplify anything basically you download on your computer, like Proton VPN, maybe Steam, but I'm not sure of that, use Electron as their core graphical user interface programming library. And every time you open a program that is written in Electron, you launch another web browser, which is Chromium. So if you're running Spotify, WhatsApp, and Brave at the same time, you're running 3 instances of the Electron, which by itself consumes sometimes more than a gigabyte of your RAM. So that leaves nothing for you to use on your computer. For example, look at my memory usage right now. It's mostly being used by Zoom and Brave, which are both Electron applications. Why? Because programmers don't want to optimize. They want to be tembel, lazy. Yeah, I forgot the word. And that brings about the destruction of the world of programming, which is a very fascinating thing to me. But the fact that it dies forces us to find new jobs. So don't think that by being a software developer, you'll form the future of the galaxy or something. No, you will not do anything more than what a moron does on his regular day. Yeah, he will earn more money than you. I'm not undermining them. I'm not underestimating them. It's just the fact that programming has turned into something of a labor rather than some kind of problem-solving technical engineering field that it was 20 years ago from now. And you might argue like algorithms, data structures are being developed every day, but algorithms is really not a part of the program. Yeah, that there are some core algorithms that every programmer needs to be aware of, but they're already set. Algorithms that come about now and to the future are products of certain fields. There are products and innovations and things within that field. For example, NASA may find a new algorithm to better detect some kind of asteroid coming towards Earth. That is not the achievement of programming, nor the job of programming. It is the job of the astronomers. Astronomers who know how to convert some kind of set of operations into a set of instructions, not programming really. Set of instructions. They just say, look at the sky and look at that from that angle, take a picture from that angle, and then blah, blah, blah, blah, and then determine whatever the coefficient the equation requires. The algorithm is part of the field where it springs from. It's not part of the programming or software or anything. So learn programming, it's a very self-improving activity. It really strengthens your ability to think systematically. Systems thinking is a very important concept, especially in today's world, because every technical or modern science or technology or engineering is modeled with systems, and programming, I think, still is the best way, not one of the good ways, best way to learn systems thinking, because computers, by a big margin, is the most complex machines that humans have ever built, and it shines most through by learning how a computer works in terms of the software layers, which we'll see in a minute by discovering how an operating system and a processor works. So learn programming, learn systems thinking. These are one of the best technical skills you can get for today's era, and in terms of philosophically understanding your way into science and other kinds of technical stuff. So iyi gidiyor muyuz? Anlamayan, sıkıntısı olan, duyamayan bir şey olan var mı?
Şimdilik iyi gibi. Çoğunu anlayabiliyorum. Anlayabildiğimi düşünüyorum.
Ben de
Sıkılan
aynı
var mı?
şekilde.
Heh, güzel. Sonunda konuşan bir kızımız oldu. Diğer kızlar ne yapıyor? Niye konuşmuyor onlar hiç? Zehra Kılıç, Meyra Özsoy, Zeynep Betül Azar.
Konuştum abi.
Eyvallah. Sağ olasın.
Belki mikrofonsuz konuşuyorlardır.
Telekinetik yetenekleri onların olabilir de bizim yok. Öyle arkadaşlar. Bir systems thinking'i öğrenin. Bu önemli bir şey. Hatta gruba da yazayım. Yani tamamen olimpiyattan şundan bundan bağımsız olarak systems thinking bilinmesi gereken önemli bir konsept. Yani iş dünyasını kovalamayı düşünüyorsanız da mesela bu açıdan düşünmek her zaman sizin olaylara bakış açınızı daha keskin, daha mantıklı, daha kategorize kılar. Ve dediğim gibi günümüz dünyası tamamen bu tarz düşünmeler üzerine kurulmuştur. Soyut düşünme üzerine değil, somut düşünme üzerine iş yapabilirsiniz günümüz dünyasında. Çünkü günümüz dünyası çok maddileşmiş durumda. Hedef odaklı gidiyorlar. En azından maddiyatta. Back to the operating systems. An operating system is Windows, is Linux, is Mac OS, is Ubuntu. All of these things you're seeing here. And don't be confused by their fancy name. An operating system may be as simple as, no, an operating system cannot be that simple because it manages processes, but what it really is that you have some kind of hardware, some kind of processor, and you have RAM, and you have your motherboard, your keyboard, your mouse, and then you have your software, your Brave browser, your Zoom, your WhatsApp, that you want to use as your software. So operating system acts as a layer between these two. It acts as a communication layer between the software and the hardware, which is ironic because operating systems are also a software, but that was a metaphorical one. What it does is, for example, I am now pressing on my keyboard JK. Once this happens, how does that reach the Brave browser? Well, first I do that, an electronic circuit inside the computer, inside the keyboard is triggered, and an electric signal by the wire is sent to the processor, which is işlemci, your Intel, your AMD, Intel i5 10300H var mesela benim sistemimde. Your CPU by a wire which is embedded into your motherboard, which you cannot see because they're all produced in terms of with the technique of PCBs, like you might see here. They're printed by meticulous machines in Taiwan. Yeah, Taiwan is the circuit producing factory of the world right now. Why can't I find a decent image? They're all very low in resolution. Yeah, that's one. Jump. So this can be your processor, and these are the wires that go through it. But of course, in your computer, this will be much, much, much smaller, the lines, because there are many, many, many more wires that need to be connected to your processor for it to work, because it's a very more complex processor than the chip we see on the screen right now. For it to run this whole computer, it needs a lot more wires, and you can access partially to these by typing out its name and looking for its reference, the documentation provided by the developer of that processor. And you see lots of stats, and maybe we can find it here. What is that? These are drivers, these are not documentations. Okay. Yeah, we're not finding those. I'm not an electronic guy, but I hope to be. Whatever. Your CPU is connected to your keyboard by a line, by a wire. And then over the wire, the keyboard sends a signal. How does it do that? It's a bit of physics and electrics engineering, which we'll not go into here, but basically it uses capacitors, which you might have recalled. In Turkish, it is kapasitör, kondansatör, swatch, as they teach it in 11th grade, whatever. So the keyboard sends a signal through that wire, and then when that set of electrons, the current, the akım, reaches the CPU, the specific circuit, which is very complex, by the way, inside the processor, triggers. We use that triggering word to describe that an event is going to happen. So don't be confused by that. It triggers an interrupt. An interrupt is basically saying the CPU stop whatever you're doing and focus on that signal that just came over here. And then it looks at the signal. It comes from the line over the keyboard. It receives the data written inside it, which you might wonder how a data is coded into a electric system. And we would say, with rather abstracting it, for example, I send a voltage of 5 volts, which will be equal to, for example, the number 1. And then I will send a voltage of 3.3, and then it will be equal to 0. And then I'll send a voltage of 4, it will be equal to 2, for example. It's a convention, but don't take my literal word for it, because it's rather more complex than that. But very basically, it works like so. Sorry, I need to answer this. Başladı mı?
Hı hı.
Başladı.
Güzel. Nerede kalmıştık? When I press the J key on my computer, it triggers an interrupt in the processor that it tells it to stop whatever it's doing and focus on that signal. Now, the signal is sent directly to the operating system. This is hard-coded in the processor's architecture. By hard-coded, we mean it is directly wired physically to be connected to the software named operating system being executed on that processor. The operating system, when it starts, introduces itself as operating system to the CPU, then the CPU enters into a mode in which it will send whatever signal from the outside it receives to the operating system direct, and then operating system receives that signal. And what does that do? It categorizes that signal. Where does it is it coming from? Is it from the keyboard, the mouse, the microphone, maybe? And so it's decides that it's from the keyboard and calls the driver of that keyboard. We mentioned the term driver here. Drivers, belki oyun oynayanlarınız bilir. Bilmem ne driverlarını işte GeForce, Nvidia driverlarının vakti geçmiştir. Ne bileyim Intel driverlarını güncellemen gerekiyordur oyunu indirmek için falan filan. Kelimeleri duymuşsunuzdur. Driver is the software that whose job is to communicate with the hardware by sometimes receiving and sometimes sending information to the hardware, and it is specific to that hardware. For example, I have a brand of Logitech as my keyboard. I may have one. It has a different driver, and the brand of Apple keyboards have a different software to deal with them. So it's not one umbrella that encompasses all of that, but there's specific ones for all of the brands, and the operating system recognizes that it's a brand of Apple, for example, and then it calls that specific driver to handle the information coming from the keyboard, and then the driver decides that the JK was pressed, and then what does it have to do now? It determined the JK has been pressed, and it looks at the events, the subscriptions. By subscriptions, we mean when a software is subscribed, it does so by writing in its own code, is subscribed into some sort of hardware or some sort of service running inside that computer, it receives notifications coming from that specific part of the system. And a service is provided by the init system, which is the first program that is run by the operating system as the computer starts, is provided that it constantly checks whether driver reported any kind of key press on the keyboard, and when it has reported one, it sends it directly to the programs that are subscribed to that kind of service, the keyboard service, so that the software, the relevant software, may be aware of the key press which it's looking for. So the J key is sent to the init process, and you might not know its name in Windows, but if you're using Linux, it's pretty part of your life. And yeah, we have system D in our system, in Linux systems, mostly as the init system. By its name, and as we already told, it is the first program to be run by the computer when it starts off, and we can see that by looking at the PS tree. This is an abbreviation for the process tree, and by process we mean that any program that is running inside that computer except the operating system and the other kind of low-level stuff like the BIOS, which is very well done. It's executing when the computer starts off for the first 1 or 2 seconds, whatever. System D is first run by the computer, and those arrows you see indicate that, for example, when the braid started, it started another braid. Like those arrows indicate that a process was started by another program. If a program was started by another program, it will have an arrow drawn to it from the program that it had been started from. Like, for example, I started XDG open and it started Zoom, and Zoom started another Zoom, and Zoom started another 144 Zooms. By the inefficiency of the programs, I meant that. Why do we need that many Zooms to be running at the same time on our computer? We may very well do that more efficiently by just doing the engineering part of the word software engineering, but we don't do that now. We just focus on serial production, whatever. Systemd first started, and it started Network Manager. Network Manager is the service. I've mentioned the service for the keyboard, and Network Manager is the front end of the server that is the service for networking, any kind of networking. It may be internet, it may be a local area network, LAN, it may be Ethernet, it may be SSH connection, it even may be a Bluetooth connection, but no, a Bluetooth connection is not a network. There's a special program for that. And you see it started Brave also. It started many Braves because every tab is another Brave, which is another example of inefficiency. XDG open is basically opening. It's a program to open all other programs, which is that, for example, I will type Telegram desktop, and if I hit enter, it opens them. I have Polkit's ID, which is a communication protocol for the top, this top bar, which includes many information about the computer, the Wi-Fi I'm connected to, the date and the time, and the charge rate. This is the program to communicate these kinds of information, and the actual program that displays these is Polybar, and we have ArtKit daemon, which is, I guess, to do with the passwords in my computer. We have systemd journal, which logs everything happening. Systemd login, which enables me to log into my computer. udevd detects any hardware that is plugged into the computer while it's running. For example, if I plug in a mouse right now, the udev will know that I plugged in that mouse and will make the other parts of the system know about that. I don't know about the user dbt. It's essentially a thing that outputs the contents of a file to the terminal. I have Zoom. I have Xbind Keys, which is the cutting application. Many things, but you see that it all was started with systemd, and we can see, I guess, the services provided by systemd right now. Systemd, systemctl status, maybe. Yeah, we have lots of services, as you can see here. We have the init, initializes everything. Network manager, as we've said, ArtKit, Polkit, dbus is another thing to do with inter-process communication. That terminal right now I'm using has to communicate with systemd to detect these mouse movements, and it must do that through dbus, the inter-process communication service. We have journald, udevd, userdb, WPA supplicant, which is to do with Wi-Fi. There are lots of brave things again, and there are other things that I don't know about. GPG has to do with the encryption, and lots of other things. So I pressed that, the operating system detected and sent it to the driver. Driver sent that to the init system, and init system can do whatever the hell it wants with that. Can do whatever the hell it wants. But again, we have a subscription system here, which these processes, these systems, like the systemd that we've mentioned, provide APIs for programs to use, by which we mean they provide a library for the computer, for the programs to use. If you've ever used Python, you might have seen that kind of statement. Whatever. that import time means get the contents of the library time into my program so that I can use it. There may be functions or special kind of algorithms defined that within that library that I want to use in my program. And every time some program uses that library, they may not want to write it from scratch. And that's a very common thing in programming, by the way. Even they include stdio.h is some sort of a library, which is the most essential library of a computer nowadays, is a library. And these services also provide libraries for programs to handle these kinds of stuff. And one of the libraries may include something like keyboard.h. And when my graphical system includes that keyboard.h into itself, it starts to constantly check whether the service has provided any kind of key presses to me. It looks for that, and when it detects something, it notificates the program that is currently running in the front end of my computer, which is in this case Brave. Like it is highlighted in purple around it, indicating it is now the focus program of my computer. And right now it is the terminal. Right now it is Zoo. Right now it's Brave again. And so it will notificate the Brave about the key press, not the Alacrity, not my terminal right over here. And now it informs him about the key press. So whatever the focus program is, it informs it about that. And you saw that I mentioned a graphical system, not that every application here tracks down the key presses of the computer individually. There's a system called Xorg in my computer. In Windows, you have Windows graphical environment. In Mac, you have Mac graphical environment, which handles all of these key presses, microphones, mouse things by itself, and informs only of the program that is focused graphically on the screen at the moment of typing the J key. So the program takes it and whatever it wants, it does. And in this case, Brave just puts that on this input bar. For Vim that is running on my terminal here, J key means to go one line down. For example, I'm pressing J right now. I'm pressing J. If we create a bunch of empty lines here and I press J constantly, it goes a line down, and I press K and it goes a line up. Whatever the program wants to do with it, it does. So as you can see, an operating system provides the software within that computer with access to the hardware through a bunch of other units in itself. But operating system is more than that. It also provides the computer with a process system, by which we mean in a computer, as we saw recently, if I may show it right. Sorry. There are lots of processors running simultaneously. I have my terminal here, I have another terminal, and I have Brave. There are lots of services, there are lots of processes. We call these processes. The programs that are currently running on the system are called processes. Not entirely, but for the purposes of this lecture, we might as well just call it. What happened to my speaking, guys? There are lots of processes running simultaneously on the system. And on a CPU, you at one time can run only one program and only one program only. There are lots of elements in this sentence, whatever. So an operating system's job is also to switch quickly between these processes for the processor to execute, so that they may create the illusion of running simultaneously on your computer. For example, for 1 millisecond, the processor will run the code of the Brave, and then for another millisecond, it will run the code of the Chrome Crashpad, and then Emacs, and then login, and then Polkit ID. To do that, for many, many, many millions of times per second, so that you get the illusion of seeing each program running at the same time, but they do not. They do not run at the same time. You might think of a program as a set of instructions, as a list of instructions. Do we have any assembly file here? Like any kind of assembly thing? Or we would just put it down here. A program is solely that, a set of instructions added one top of into another, and CPU starts from the top, goes to the bottom, executing every line in the on the process. So, for example, an operating system will bring up the assembly, which is coded in binary in the computer, by the way. It will bring that to the CPU, and then CPU will, for example, execute the first 5 lines of that thing, and then the operating system will kind of capsulate it, take it and quarantine it in some part of the RAM that is untouchable by any other process. And also this untouchableness is also provided by operating system. It will not allow any program to access another program's RAM space, so that no hacking can happen and no malfunctioning can happen. And then it will move on to another program, and it will execute the next 5 lines of that program, and it will move on to the other, and then it will continue in a loop unless an interrupt is triggered, which we have mentioned at the beginning of our explanation of how a keyboard works. You press a key and there's an interrupt triggered, and all of the execution just stops. As we said, processor stops whatever the hell it's doing, and it looks at that signal, handles with it, sends it to the driver executes some line of code, and that processor goes back to the program it ran before the signal came to its wires. So that's how a computer works at a very basic level of understanding. It's much more complex than that. And once we look at the CPU architecture, it becomes even more complex. But before that, as you probably have realized, we have computers built on top of abstraction over abstraction, by which we mean abstraction layers. An abstraction layer may be defined in various other ways, but basically you have hardware, and there's a program called operating system that handles with hardware and gives its output to you in a understandable form, so that you can handle with it without worrying about how the hardware works. The brain right now I'm using is not aware of what kind of brand my keyboard is. It is not aware of that. It just knows that the JK was pressed. It even does not know which one of the keys was pressed. It just gets the signal that the key representing J was pressed. For example, if my keyboard layout was entirely different and the JK was at top right bottom, whatever the hell is that, top right, and I press that, and now I'm pressing J key, the brain would not know the difference, and it will only know that the JK was pressed. It would not know its location on the keyboard. It would not know whether its LED is lightning or not. These are the jobs of the operating system, so it does that. It is no concern of the brain to know the details of how hardware works, the signaling procedure, the protocols it uses to communicate its data, and the electricity levels, the voltage levels it uses to communicate its data. It only knows the JK is pressed. And the operating systems is business of nothing to know what the hell is Brave doing with that key. It does not work like that. So an abstraction layer is kind of a layer that, makes you forget whatever is going on before you, like if you're Brave and operating system is before you, the hardware is before that, you don't know anything about what's happening there, and you only focus on your input and your output and your code. Nothing other than that is of your concern. So that's why programmers do not need to learn how a CPU works in detail in order to program some things, because they do not need to know that. The operating system handles it for them. And an operating system developer doesn't have to know how a transistor works, because the electronics engineers had already handled how a transistor works. So an operating system developer has to only know what kind of voltage levels the processor uses to communicate its data so that it can apply the proper voltage to communicate with it. It is of no concern of the operating system to know what's going on inside a processor. It only must know how it outputs and how it must interpret the outputs of the processor. The processor's inner workings is none of the operating system's concern. It must only know its inputs and outputs, how to communicate with it, and how to understand it. That is the basic idea of a program, actually. A program or computer is basically the same thing, is modeled by its input, by its output, and the code it runs. The machine is modeled by these three terms and nothing more than that. Okay? So abstraction layers, as you can see, are pretty important to develop any kind of computer, because computers are such complex machines that to develop Brave with having to worry about the inner workings of the CPU or the operating system, doing it all in one go would be a lot harder than it is today, and maybe impossible. You build the computer from the scratch in all to the very end, running Brave. You cannot imagine that one building a computer from scratch. Abstraction layers provide us with ease and modularity also. Because if abstraction layers did not exist, if an operating system's sole purpose was to run Brave, then for each program we needed to get another PC, which would be very expensive. So it brings about the modularity and the beauty of programming. You may have one piece of a computer that is used for everything in that computer. Every task utilizes that in a different manner. Abstraction layers provides us with that, and also modeling how a computer works. As you realized, while explaining how a keyboard works, we first said the signal comes into CPU, and the CPU outputs this, and then the driver does this, and then the system does this, and then the Brave does this. We built layers upon layers on how a key press just works. Computers are just like that. They're layers upon layers of abstraction that eventually goes to one single task. And there are many abstraction layer pyramids inside a computer that eventually does whatever the job you're trying to do right now. Computers can be modeled as simple as that, because the model has to be simple in order to operate in such a complex machine. And you can scale it down or up, this abstraction layer concept, on every part of the operating system. The computer, the inner structure of a CPU, the inner structure of a transistor, the inner structure of a chip inside the CPU, and then also the computer's main architecture, which is CPU and the RAM and the SSD and the microphone or something. And then you can expand this into the operating system. You can expand this into the services. And then individually, you can also model them like that. The Brave in its software architecture may be modeled by abstraction layers over abstraction layers. You can put many abstraction layers to model one single computer running on your desktop. And that's the beauty of how we do things around here, which is exemplified by this beautiful diagram here. You see, this is the standard architecture, von Neumann architecture, for how a computer should be, which is applied by most of the computers today. A CPU has to be existent, which is actually the computer itself, the thing that computes whatever it is you're trying to compute. The CPU's abbreviation for central processing unit. So it's a unit that is central and processes, basically computes things. And in it, it has registers which are temporary storage locations. Combinational logic basically means the computing part, and this is actually the actual processor, and we have a control unit beside it that times the inputs and the outputs of the CPU, because each input cannot come at the same time to the CPU. They must be aligned in a line to wait their time to be executed by the CPU. And then beside that, we must have a main memory, which is more commonly known as RAM, random accessible memory, that the CPU will use to store the program data while it's running for the programs to be able to store variables. For example, you see while in programming, we are going to use a lots of variables. You may exemplify one here. A equals 1, and then print A. Once we do that, we print 1, and A is stored in RAM while the program is running. And then whenever the program wants, the CPU accesses for the program so that the program can operate on this thing. So we require a main memory, a RAM, to be around to execute our program, and we have input and output devices. A computer architecture can be at the most basic level modeled be like so. There are input devices which are keyboard, mouse, microphone, etc. There are output devices like your monitor, your speakers, your I don't know, your laser pointer that you put on your computer. And then there's your CPU that handles all of the jobs, and a RAM to store its data while it's running. The computer is basically that. The other things are all built on top of this beautiful, simple, yet effective organization of simple machines to create a more complex machine in the end. So how are you feeling right now? Are you understanding the lecture? What's going on around there?
A bit of.
Nasıl?
Ya şimdi bir şeyden sonra odaklanmakta yani zorlanmaya başladım. Hep İngilizce olunca
Anlamadığınız yerde durduğunuz sorun oğlum. Niye durduruyorsunuz?
yok ya zaten bildiğim şeyler olduğu için şey yapmadım da.
Bence kafamızda bir şeyler oluştu yine de.
Evet.
Aynen genel konuyu anladık da biraz detayları kaçırabiliyoruz yani.
Aynen.
Detayları boş verin. Asıl olayı anlayın. Bizim için önemli
Ya
olan o.
maşallah çok hızlı konuşuyorsun. Tutturamıyorum.
He?
Çok hızlı konuşuyorsun diyorum.
Ne kadar kızı konuşuyorum. Oğlum, Türkçe konuştum mu? Konuşmamıştım.
Tamam da işte ben hazırlık daha o seviyede değilim. O yüzden diyorum.
Hazırlık mısın sen?
Evet.
Başka hazırlık olan kim var burada?
Ben varım bir de.
Sadece ikiniz mi? Başka yok mu?
Diğerleri
Ben
aciliyse belki daha iyi anlıyordur.
Ben mesela
ben
10. sınıfım.
ben de varım. Hazırlığım.
9. sınıf yok mu?
Ben 9'um.
Hı. 11 yok herhalde hiç.
Ben 10. sınıfım mesela.
Güzel. Farklı sınıflardan arkadaşlarımız var. Bazıları çok erken, bazıları şey. Bu arada ekranda ne yaptığımı sorarsanız bir C programı yazdım küçük. Onun assembly'sini göstermek istiyorum size. Assembly
Her şey
çevirmiş halini. Assembly arkadaşlar bilgisayarın en temel programlama dilidir. Programlama ilk çıktığında
Abi
eee,
anlaşılabilir en alt seviye şey değil miydi? Hala insanın anlayabildiği en son.
aynen öyle düşün. İlk başta bilgisayarlar ilk çıktığında bu Alan Turing falan zamanında programları şöyle yazıyorlar arkadaşlar. Şu Bu nedir? Bunlar kağıt ve kağıdın bir kısmını deliyorlar. Delikli kağıtlar bunlar. Mesela atıyorum deldiği yerler bir, delmediği yerler sıfır gibi düşünün. Böyle bir sıfır yan yana yan yana bir sürü alt alta kod olmuş oluyor ve şunun gibi düşünün. Bilgisayar diyor ki şunu gördüm mesela, ha diyor ben toplama yapmam lazım. Şu sıfır oldu, çıkarma yapmam lazım. Şu bir oldu, ha bu çarpma yapmam lazım. Bunlar işlemcinin içinde hard coded biçimde bulunuyor. Siz bunları sırayla veriyorsunuz bilgisayara. Bilgisayar sırayla yapıyor. İlk başta böyle programlanıyordu. Sonra herifler diyor ki ulan tüm programı böyle tekrar kağıt dele dele yapmak bir tık zor sanki diyorlar. Assembly diye bir şey ortaya çıkarıyorlar. Assembly'nin de bundan pek bir farkı yok ama gene en azından klavyede yazarak ulaşabildiğiniz bir şey. Tabii o zamanlar monitör dediğimiz şey yok. Bu typewriter'lar var ya, daktilolar. Daktilolarda yazıp şeylerde çıktısını alıyorlar. Yazıcıda çıktısını alıp görüyorlar. Kodu doğru yazıp yazmadıklarını. Oradan anlıyorlar. O yüzden hani şurada push Q yerine bir C yazsam buradaki Q yerine gitti yani. Tüm program gitti. Her neyse bu assembly'yi ortaya çıkarıyorlar. Bu assembly en basitçe ne biliyor musunuz? Hani dedim ya böyle alt alta tüm instruction'lar, kodlar yazıyor diye. Bunun yazıya geçirilmiş hali. Yani arada hiçbir başka değişim yok. Yani önceden şu vardı burada. Tamam mı? Onun yerine bu geldi. Yani bu yazıyla geldi ki assembly programında zaten direkt çalıştıramazsınız. Bunu bir assembler denen bir programa vermeniz lazım. O bunu en son binary haline yani bir sıfırlardan oluşan bilgisayarın anlayacağı hale çevirecektir. Şu an ekranda gördüğümüz tabii 64 bit modern Intel assembly'si. Şu an benim bilgisayarımdaki işlemciye göre hazırlanmış assembly. Çünkü her işlemcinin assembly'si farklıdır. Bunu da şuradan görebilirsiniz. Kendi işlemcim benim. Instruction set yazarsanız o işlemcinin anlayabileceği tüm kodları görmüş olursunuz. Ben bugün niye dokümantasyon bulamıyorum? Bunu ne user review?
Başta açtım. Ryzen 5 mi daha iyiymiş? i5 mi?
Sinir
Bir
oluyorum
şey
var ya bak en
sorabilir
son.
miyim?
Ha sor.
Anlayabileceği kodlar derken ne demek istedik?
Mesela şöyle düşün. 101 yazdım ben buna. Bu bundan toplama yapması gerektiğini anlıyor, tamam mı? Ama başka bir işlemciye 101 yazsam bundan bölme yapması gerektiğini anlayabilir. İşlemciden işlemciye değişir hangi sayının neye karşılık geldiği.
Hmm.
Anladın mı?
Tamamdır, sağ olasın.
Bu instruction set'i nereden görebiliyorum? Bir ara bakıyordum ben bunlara.
Onlar
Biraz
çok low level olduğu için biraz zor.
şöyle oluyor bak şöyle
Program
düşün.
halinde.
10.000 sayfalık bir instruction seti vardı bu benim işlemcim. 10.000 sayfa. Tabii İlk çıkan
Yani
işlemcilerde böyle
10
değil. 10-15 tane var. Sonradan gelişiyorlar bu hale dönüyorlar. Bu push Q şey yapar. Register vardı ya işlemcinin içerisindeki geçici depolama üniteleri. Onlara veri yerleştirmeyi sağlar. Move Q register'lar arasında git gel yapar. Bu sondaki Q ve L'ler şeyi ifade ediyor. Taşınan veri tipinin sayımı işte 64 bitlik sayımı 32 bitlik sayımı o olup olmadığını söylüyor. Bak burada call diye bir şey var. Şuna dikkat ederseniz. Call demek bir tane kütüphanede bir fonksiyon varmış. Onu getir çalıştır demek. O printf diye bir fonksiyon varmış. Onu getir bizde çalıştır demek. Tabii bunun öncesinde printf'in argümanları var. Yani bak şurada argüman verdik ya buna şu sayıyı yaz diye. O argümanları bir yere koymamız lazım ki adam bakıp ha benim argümanlarım buymuş ben bunun üzerinden işlem yapacağım desin. Onları da şurada gerçekleştiriyoruz. Register'lara koyarak o verileri burada gerçekleştiriyoruz. En son burada da leave ve return'ümüz var. Bunları çok takmanıza gerek yok. Ama hani bir görün diye açtım bunu. Assembly bu demek. Compiler'ların yani bilgisayar bu programlama dillerinde yazılan kodları bilgisayarın anlayacağı şeye çeviren programların görevi budur. Önce programı assembly'ye çevirirler bu şekilde. Assembly'den sonra da bilgisayar koduna çevirirler ve şey yaparlar. Nedir onun adı? Linker programını çağırırlar. Linker demek bu en başta kütüphanelerden bahsetmiştik ya. Hani ben bir kütüphanede bir fonksiyonu yazdıktan sonra onu farklı farklı programlarda aynı anda kullanabilirim diye tekrar tekrar kütüphanedeki o fonksiyonu her program için ayrı ayrı yazmak zorunda olmayalım. Linker bu kütüphanedeki fonksiyonları alıp en son kod halinde o son programa yapıştırmakla görevlidir. Yani evet, bayağı o kütüphanenin hepsini, tabii 0-1'lere çevrilmiş haline alıyor hepsini ve buraya en başa tabii yapıştırıyor. Buna static linking diyoruz. Dynamic linking dediğimiz bir linkleme türü daha var. O da diyor ki o tüm kütüphaneyi yapıştırmak yerine şu en başa bir ibare koyuyor. Diyor ki işletim sisteminin şurasında bir yerinde şöyle bir kütüphane olacak. Onu oraya koyuyor, bırakıyor. İşletim sistemi de programı ilk çalıştırmaya başladığında o ibareyi görünce gidiyor o kütüphaneyi kendi bünyesinde arıyor. Bulduğunda bu program RAM'e alınacağı zaman RAM'deki kısma yapıştırıyor. Böylece diskinizde boş yere yer tüketmiş olmuyorsunuz. Burada bir implikasyonumuz vardı. Evet, programlar çalıştırılacaklarında tüm kod baştan sona kadar satırlarca ne kadar satır olursa olsun tüm kod anında RAM'e alınır ve RAM'den direkt işlemciye tek tek gönderilir. Çünkü işlemci çok hızlı çalışmak zorundadır. 4.5 GHz'lik bir işlemcim var dersi mesela. Bu ne demek? Saniyede 4,5 milyar tane pardon işlem yapabilir bu işlemci demek. 4,5 GHz. Yani 4,5 milyar defa sen iki sayıyı toplayabilirsin bir saniyede o işlemciyle. Yani bu kadar hızlı olması gerektiği için her şeyin RAM'den gitmesi lazım. RAM çok register'lardan sonra işlemcinin en hızlı veriyi alabileceği kaynaktır. Depolama alanı ondan çok daha yavaş veriyi gönderir. O yüzden işletim sistemi en başta depolama alanından tüm kodu alır, RAM'e yapıştırır. Ondan sonra işlemleri başlatır. Random Access Memory denmesinin sebebi de şudur. Bazı belleklerde yani depolamalarda yani memory'lerde şöyle bir kural vardır. En başta RAM'in en yukarısındaki veriye erişebilirsin. Sonra ikinci satır, sonra üçüncü satır, sonra dördüncü satır böyle sırayla gitmek zorundasındır. RAM'de böyle bir şey yok. İstediğin yere istediğin zaman ulaşabilirsin. Yani o yüzden programı illa en başa koymak zorunda değilsin. En sona koyarsın, ortaya koyarsın, böler koyarsın. Hiç sorun olmaz. ROM diye de bir kavramımız var. Read Only Memory. Bunlar adından da anlaşılacağı üzere editlenemeyen, içindekiler fabrikasyon sırasında yüklenmiş ve değiştirilemeyen bellekler. Bunlar genelde içine BIOS yüklenmesinde kullanılır. Şu anki BIOS yüklenen ROM'lar aslında editlenebilir ROM'lar ama adı tarihi olarak ROM diye kaldığı için biz de ROM demeye devam ediyoruz. Ee, Onlar genelde bilgisayarlarda BIOS depolamak için kullanılır. BIOS nedir? Basic Input Output System. Bilgisayar ilk başladığında ilk başlattığı, ilk işlemcinin çalıştırdığı kod BIOS kodudur. Otomatik olarak BIOS kodunu RAM'e yükleyip çalıştırmak üzere dizayn edilmiştir. BIOS kodunun da görevi basit bir donanımda bir sorun var mı, çalışabilecek durumda mıyız diye bir kontrol yapmak. Bakın BIOS o kadar teknik bir program ki işletim sisteminden bile daha teknik ve daha düşük seviye. Yani low level yani donanıma yakın bir program. Donanımda bir hata var mı diye kontrol ediyor. Sonrasında da işletim sistemini çalıştırıyor. BIOS'un ki günümüzdeki yeni adıyla UEFI'ın Unified Extensible Firmware Interface'in görevi bunu yapmak, işletim sistemini başlatmak. Bu bilgisayarınız ilk açıldığında gördüğünüz siyah ekran, bilgisayarın modelinin ama markasının logosunun çıktığı ekran, işte BIOS'un getirdiği ekran. Veya BIOS settinglere giren vardır aranızda. Onlar gene BIOS programının sağladığı şeyler. İşlemci ilk kendine güç geldiği anda ROM'da ne varsa onu kopyalar RAM'e, onu çalıştırır. Zaten o çalışması bitmeden önce diski tarar ve takılı USB'lerde, SSD'lerde, HDD'lerde herhangi birinde bir işletim sistemi var mı diye bakar. Buldu mu ilk bulduğu işletim sistemini yükler. Bu ne demek? İşletim sisteminin kernel'ını yani çekirdeğini, en çekirdek kısmını ki Linux'ta bir işletim sistemi kernel'ıdır. RAM'e yükler ve işlemcinin instruction pointer'ını yani sıradaki çalıştıracağı kodun adresinin yazdığı register'ı işletim sisteminin ilk kodunun bulunduğu adres olarak değiştirir. Aslında baktığınızda çok basit bir işlem. Ve işlemci hiçbir şeyden haberi olmadan garibim BIOS'un çalışmayı bıraktığında haberi olmadan bir anda işletim sistemini çalıştırmaya başlar. Ki işletim sistemi yazarları da işlemcinin direkt BIOS'tan böyle hazırlıksız bir halde geldiğini göz önünde bulundurarak ilk çalışacak kodlarını dizayn etmişlerdir. Linux'un kaynak koduna bakabilirsiniz internetten. Bakın sayfalarca kod var burada. Bunlar bakın init sistemleri, IPC yani Inter Process Communication kütüphaneler, en temel kütüphaneler tabii. Bunların üzerine kendi kütüphanenizi kurabilirsiniz. Rust entegre etmeye çalışıyorlar. Yeni bir programlama dili bu. Sesle ilgili yani mikrofondur, şudur, budur şeyler. Virtualization ileri bir konu. Bunlar bunlar build etmeyle falan alakalılar. Scriptleri var, security, güvenlik. Şuradan kernel, driverlar bak. Mesela bazı driverlar direkt işletim sistemiyle gelir. En çok driver'la gelen işletim sistemi de Windows'tur bu arada muhtemelen. Ama burada da bayağı driver'ımız var. Yoksa da zaten kuruyoruz. Sertifikalar var internete erişmek için mesela kriptografi. Kernel'a girelim. Ben de bu arada çok bilmiyorum bu source kodu. Yani anlaması da zor. Bayağı ileri bir konu. Kernel üzerinde çalışıyorsun demek. Yani programlamanın peak noktasına ulaşmışsındır demek. Burada mesela programlama dili bilmek değil. Burada mesele bilgisayarı bilmektir. Bunu yazabilmek. Mesela CPU diye bir program var burada. Ne işe yarıyor bilmiyorum. Bir şeyler yapıyor. Artık ne yapıyor bilmiyorum. Bir şeyler yapıyor. Güzel dokümantasyon da var aslında. Birazcık işletim sistemi teorisi bilsek anlarız muhtemelen. Çekirdek meselesine de değinelim kapatmadan. Çok çekirdekli işlemci demek arkadaşlar aslında işlemcinin içinde bir sürü işlemci demek. Hepsi aynı anda farklı bir programı çalıştırdı demek. Ya bu sadece günümüzde işlemcileri daha güçlü yapmak için kullanılan bir hile. Bir işlemci içine birden fazla işlemci ekliyorsunuz ve işletim sistemi sürekli bir tane işlemcinin de o programları switchlemek yerine aynı anda 4 işlemcinin gücünü birden kullanmış oluyor. Ama hepsi aynı RAM'e bağlı. Register'ları ve kontrol üniteleri farklı yani öyle. Efes var bu file system muhtemelen. Evet öyle. Driver'lar. Bak Bluetooth driver'ları. Şu an benim bilgisayarımda bu çalışıyor mesela. Bu kod çalışıyor. Kodlar çalışıyor. Burada bir sürü. Bunların hepsini bir insan oturup yazmak zorunda. ext4 var. Benim bilgisayarımdaki dosya sistemi. FAT'ı bilirsiniz. Ee, Neredeyse her flash'ta, buzdolabında, dünyada görüp görebileceğiniz cihazların %90'ında kullanılan dosya sistemidir. Öyle bakalım file'ın içinde ne var. Çok low level stuff bunlar. Her neyse. İnşallah dersi beğenmiş, faydalı bulmuşsunuzdur. Bir
Sen
şeyler
de
öğrenmişsinizdir, bir şeyler diye ümit ediyoruz. Dediğimiz gibi ağırdan alacağız dersi. Bilgisayarlar hakkında ekstra şeyler öğrene gideceğiz. Madem düz programla öğrenip geçişelim istemiyorsunuz ki zaten öyle yapsak kısa sürer. Ee, Böyle devam edeceğiz. Buna itirazı olan başka bir yol isteyen var mı?
Şey diyeceğim. Bundan sonra hep şey mi? Bu şekilde mi ders işleyeceğiz? Yani matematik kısmını tamamladık mı yoksa bir ondan mı?
Matematik kısmında bizim bir işimiz yok. Ama C öğrenirken arada sıkıştırabileceğimiz ufak detaylar sıkıştıracağız. Öyle düşün.
Hı hı, tamamdır.
Ben şey diyeceğim. Sonraki dersimiz yarın mı yoksa haftaya yine aynı saatlerde mi olacak?
Yarın da dersimiz var.
Kaçta?
Aynı saat.
Tamam.
Bir sorusu, görüşü, bir şey olan yok mu?
bir şey sorabilir miyim?
Elbette.
Biz C dilini mi öğreneceğiz?
Evet. İyi, kusura bakmayın gecikme için. Heh,
Yok estağfurullah.
Görüşmek üzere. Hayırlı akşamlar diliyorum.
İyi akşamlar.
İyi akşamlar.